Your test says the groups differ, but how big is that difference? Epsilon-Squared, the effect size for the Kruskal-Wallis test. Imagine customer satisfaction ratings at 3 store branches on a 1 to 10 scale. Downtown tends to score lower, the flagship scores higher, but the groups clearly overlap in the middle. The medians climb from 5 to 6 to 7.
The key idea. Kruskal-Wallis ranks all 30 ratings from lowest to highest, then adds up the ranks inside each branch. Those rank sums come out to 93, 155, and 217. If the branch didn't really matter, the sums would be roughly equal, so the bigger the gaps between them, the stronger the effect. And because it works on ranks, not raw scores, it stays robust to outliers and skew. Now, the test itself gives an H of 10.39 with a p-value of 0.006, so it's a real difference. But how large is it really?
The formula. Epsilon-Squared is just h divided by n-1. We plug in that h with 30 ratings in total, and it works out to an Epsilon-Squared of 0.36. Think of it as the share of the variation in ranks that your grouping explains, on a scale from 0 to 1. There's also a bias-corrected cousin, eta-squared based on h, which gives 0.31. Same story. How to interpret it? Anything below 0.01 is negligible, then small, then medium, and above 0.14 is large. Our 0.36 lands well into the large range, a substantial difference between the branches.
Why it matters. The p-value only tells you whether there's a difference at all. The effect size tells you how much that difference actually matters. With a big enough sample, even a trivial gap can come out significant, and that's exactly the trap Epsilon-Squared helps you avoid. When to use it. Reach for Epsilon-Squared when your outcome is ordinal or skewed, and you've run a Kruskal-Wallis test. If your data is roughly normal, use eta-squared with ANOVA instead. Try it free at MetricGate.com.